Hi, I'm Aki Kawamura. I'll be talking about my work on the density conjecture for pinwheel scheduling. We have k tasks, and we select one task to perform each day. Each task I comes with a number a sub I called its period, and it means that this task must be performed at least once every a sub I days. For example, in this instance, the red task must be performed once every 2 days, while the blue and yellow must each be performed once every 4 days. In this case, we can satisfy all constraints by performing the red task every other day, and on the remaining days alternately performing the blue and yellow, thus repeating this 4-day sequence. So we say that the instance 244 is schedulable. What about 234? That's obviously unschedulable because we must perform the red task at least half of the time, the blue task 1/3 of the time, and the yellow 1/4 of the time, and the sum exceeds 1. The total workload is simply too large. The converse is not true. Having the sum of the fractions less than 1 doesn't imply schedulability. For example, replacing the 4 in this instance with 6 or any larger number makes the sum less than 1, but the instance remains unschedulable. To see this, consider the yellow task with period 100. It's an infrequent task, but you'll need to do it at some point. But then you'll need to perform the red task in both the previous day and the next day, and you've already missed the blue task for 3 days. How about this instance, 3458? Again, let's start with this least frequent task, the green one with period 8. Because the red task is period 3, you must do it either the day before or the day after the green task. Let's say you do it the day before. You still must do it again within 2 days after the green. But within the same 2 days, you must also perform the blue task because otherwise you'll miss it for 4 days. So these 2 days must be either blue-red or red-blue. In any case, you have a 4-day interval with no yellow. Since yellow has period 5, you must schedule it in both sides of this 4-day block. Now you see a 3-day block with no blue, so you must schedule blue just before and after it. So this other one is red, and also this leftmost day must be red. And now, if you're careful, you see that repeating this 8-day sequence satisfies all constraints. So this is a yes instance after all. As we have seen, finding a schedule can be tricky. The task with period 3 sometimes needs to be performed in 2 days, suggesting that the problem is not entirely trivial. Now, here's something that is fairly trivial. Once we know that this 3458 is schedulable, it follows immediately that 3468 is also schedulable. Because if we schedule something every 5 days, that's already a schedule that does it every 6 days. In other words, schedulability is preserved by the operation of relaxing an instance, which means increasing one of the periods. Here's another property. Now we change the instance to 45668 by replacing 3 by 2 copies of 6. This operation of splitting a task into 2 tasks with twice the period also preserves schedulability. To see this, let's call the 2 new tasks 6A and 6B, and assign the slots we used to assign to task 3 in the original schedule to 6A and 6B alternately. Then, naturally, both A and B appear at least once every 6 days. Now, although this problem is known as pinwheel scheduling, it doesn't by definition require that the solution be a repeating schedule like this. Nonetheless, it's easy to see that any schedulable instance has a repeating schedule. Let me explain using this example. Each time we perform the red task, its lifetime is reset to 3 days. As days go by, it decreases to 2 and then to 1. Our goal is to keep resetting the lifetime before it ever reaches 0, and likewise for other tasks. Now look at this vertical vector of numbers and call it the state on that day. For example, this 1427 means that we must perform the red task immediately because it has lifetime 1, while we have 4 days to perform the blue task because we have just performed it. If we perform the red task now, then on the following day, the red lifetime is back to 3. The yellow lifetime has fallen to 1, so we must do yellow next. Now there's no task with lifetime 1, so we may do either red or blue. In this way, we can build a state transition graph, indicating which states we can go from each state. Schedulability means the existence of an infinite walk in this graph, or equivalently, a cycle that we may traverse over and over. So, given enough time, we could decide schedulability simply by building the graph and looking for cycles. But today, we're interested in easier conditions that are necessary or sufficient for schedulability. Let's start with the obvious necessary condition discussed earlier. The sum of the reciprocals of the periods is called the density and is denoted by d. As we saw before, having a density at most 1 is a necessary but not sufficient condition for schedulability. But there are some special cases in which this condition is sufficient. Starting from the bottom of the slide, one such special case is when there are only two distinct period values. It's been shown that such an instance is schedulable unless its density exceeds 1. Another such special case, which is actually easier, is when each period is a multiple of the previous period, like this example. One way to see this is that such an instance can be obtained by the splitting operation I mentioned, starting from an instance with a single period value, like this 444, which is clearly schedulable as long as its density is less than 1. Now, an interesting corollary of this is that if an instance has density bounded by 1/2, that is, if the overall workload is pretty small, as in this example, then it's unconditionally schedulable. To see why that's the case, consider rounding down each of these 5 periods to the nearest power of 2, like replacing 6 by 4. This reduces each number by a factor less than 2, which means it increases the density by a factor less than 2. Since the original density was at most 1/2, the new density is at most 1, allowing us to apply the theorem on the left, so the original instance is also schedulable. Now, this corollary offers a valuable lesson. It's good to keep your workload to a moderate level so you have plenty of leeway to cope with different kinds of tasks. But that brings us to a natural question. Is it really necessary to restrict your workload to as little as half the full capacity? As it turns out, it is possible to push this boundary a little bit while retaining the guarantee of schedulability. We can already see that the factor of 1/2 leaves some room for improvement. We got this factor when we rounded the periods down to powers of 2. But we didn't really need to use powers of 2 exclusively. All we need to apply the theorem is that each period be a multiple of the previous one. In this case, the original instance starts with 6 and 12, so why don't we instead round it down to something like 6, 12, 12, 24, 24? That would save us a lot of the unwanted increase in density. Moreover, we don't really need to rely solely on this first theorem, which eventually turns everything into a single period value. According to this other theorem at the bottom, it's fine to end up with two distinct period values. So, if we take that into account and devise better strategies for rounding down, it turns out that this factor of 1/2 can be increased to 2/3, as was shown a few years later by this paper. That pushed the factor up from 0.5 to 0.66, and these folks conjecture that in fact it could be increased to 5/6. Now, what's this number 5/6? It's the density of the instance 2, 3, a huge number, which we saw was unschedulable. That means the factor cannot be increased beyond 5/6, and the conjecture says that it can be increased all the way up to 5/6. This conjecture was taken up by many people who succeeded in raising the factor to 0.7 and then to 7.5. In addition, the 5/6 conjecture itself has been verified in a number of special cases. For example, in this last paper, they conducted computer experiments to verify the conjecture for 12 or fewer tasks. Today, I'm happy to report that I've been able to establish the conjecture in full generality. Like some of the previous work, my proof involves exhaustive checking by computer. But of course, the conjecture itself is about infinitely many instances, so exhaustive checking cannot be our only tool. So, in the rest of my talk, I'll tell you how I reduce the theorem to finitely many instances to check. Here's the statement again. If an instance A has a density at most 5/6, then A is schedulable. We can't check all the infinitely many instances A, so instead I used my computer to establish this lemma. Just like the theorem, the lemma says that low density implies schedulability, but it asserts this only for instances B containing periods at most 22. That means we have only finitely many B to check, which is good news for my computer. Bad news is that the criterion for low density is now slightly relaxed. It's now 5/6 plus 1/22. Moreover, we are using a slightly modified version of density d prime, which is calculated by regarding 11 as 12, 12 as 13, and so on. Despite these changes that bring in more instances B, it turns out that the lemma remains true, and it was verified by brute force checking of about 25 million instances B. By the way, the lemma does become false if we replace this 22 by a smaller number. The theorem would still follow from that version of the lemma, and it would be nicer because it means less computation, but the lemma simply fails. We get counterexamples. That's why I have this magic number 22 here. Anyway, to show how the theorem follows from this finite lemma, let's suppose that contrary to the theorem, there exists an unschedulable instance A with density at most 5/6. From this, we'll construct a counterexample to the lemma, that is, an unschedulable instance B containing only periods up to 22 and having density only slightly bigger. For that purpose, we'll eliminate large periods from the instance by applying the following two operations, which I will explain by example, starting with this instance A on the top. Operation 1 is to reduce the largest period in the instance. In this case, we reduce 87 to 51 to align it with the second largest period. Next, operation 2 combines two identical tasks into a single task with half the period. In this case, the two copies of 51 become a 25. We repeat these operations over and over until our instance contains only periods of 22 or lower, and this will be our instance B. These operations are just the inverses of the two operations mentioned before, so they preserve unschedulability. Now let's look at the process again to see how it affected the density. The density of the original instance A was the sum of the heights of these bars. We've then applied the operations to get rid of the tasks below this threshold. Our first application of operation 1 replaced 87 with 51, increasing the density by the amount indicated by the orange arrow there. Then operation 2 simply combines two tasks into one and leaves the density unchanged if we ignore for now the effect of rounding down. The next application of operation 1 grows the lowest bar by that much, and once again operation 2 just combines two tasks without changing the density. So the total increase in density is indicated by these orange arrows combined, and hence is less than 1/22 as we claimed. But that was if we didn't round down in operation 2, and as a result the 12 in the final instance B, as in this example, remained 12.75. That's why we had to state the lemma for the modified density d prime, which regards any 12-ish number like this as a 13 to be on the safe side. As problems for future work, first of all, I would love to find a human-readable proof that didn't rely on computer calculation. The computational complexity of deciding schedulability is also wide open. It's not even known whether the problem belongs to NP. It's also unknown whether the problem is NP-hard. The problem we have considered here is, in a sense, a packing version of pinwheel scheduling, in which we try to put the red, blue, and yellow tasks into Z, the set of integers. We also have the complementary covering version of pinwheel scheduling, where task I, or perhaps activity I, can only be scheduled at most once out of every a sub I days. In this case, complementary to what we said, an obvious necessary condition for schedulability is that the density be greater than or equal to 1, while the density greater than 2 is a sufficient condition. This naturally raises the question of precisely where between 1 and 2 the threshold for sufficiency lies. In this case, the gap is still open. Our pinwheel scheduling problem is only the simplest of the many settings we could consider. It may also be recast as optimization problems, of which the simplest is known as bamboo garden trimming, which amounts to asking in our problem to minimize the maximum factor by which we violate the frequency requirements. My new result today yields a slight improvement in the approximation ratio for this problem, as I discuss in my paper. The problem may also be modified in various ways to bring it closer to practical situations. For example, there may be multiple workers to perform tasks, or different tasks may require different amounts of time to perform, or switching from one task to another may consume some amount of time. These variants have been actively studied by researchers in the field of real-time systems. It's interesting to ask how broadly our ideas of theoretical analysis might be applied to these more complicated situations. Thanks for your attention.